But this is, so you just heard basically all about CO2 and all about a biologist's perspective of CO2. And so what I want to do is I want to give you a little bit different perspective. I want to give you a perspective from a chemist's point of view, not from a biology point of view. And the other thing you want to just keep in mind is that I am not a climate change, global warming expert in any way, shape, or form. I just am giving my chemical background to something, so I know a little bit about it. So I'm going to talk about that, but keep in mind you have to take everything that I say with a little bit of grain of salt because I'm not an expert in this area at all. Okay? So first thing I wanted to do is I wanted to find probably one of the most offensive opening slides I could find on the internet. And so this one kind of struck my fancy. And again, this is probably from some kind of biologist's opinion, right? It's saying that the world is coming to an end, right? Because global warming, and what causes global warming, you can't really see it here, it's a little bright. But there's a person's hand here holding the earth, and the earth is on fire. Okay? Why is a person's hand holding the earth? Because global warming is caused by humans. That's the whole point of this slide, right? And that is a very politically charged statement, right? Because that's what's going on in Congress right now and in the White House and all that stuff. They're going to fight over this stuff, and in fact, they didn't really fight. They just said that's not real. So, but that's a political issue as opposed to a scientific issue. So today, we're going to look at a little bit of a scientific issue with regards to that. Okay. So first thing is, from a chemist's point of view, what is global warming? What is the greenhouse effect? Okay. Well, it depends on where you are. So we're on the Earth. If we were on Mars, it'd be a completely different thing. Mars basically has no greenhouse effect at all. And I'm not talking about change in greenhouse effect over time, which is what Dr. Jan was talking about. I'm talking about just the greenhouse effect at all. So why does Mars not have basically any greenhouse effect at all, but the Earth does? Anybody have any ideas?
The lack of strong atmosphere.
Yeah, exactly right. It lacks an atmosphere. So in order to have a greenhouse effect, you have to have an atmosphere. Why? Because you have to trap the heat that's coming from the sun somehow into that planet, into the atmosphere. And that's what this slide is all about. So this slide shows you that you have stuff coming from the sun, light coming from the sun. What kind of light do you have coming from the sun? Well, you have ultraviolet, and we know that because what does ultraviolet do? What does it cause? Sunburn, right. So ultraviolet causes sunburn, so you get sunburn, so there's ultraviolet light coming in. And we also know there's visible light coming in because I didn't stub my toe coming in here today, right? I could see where I was going. And so those are the two main types of light coming from the sun. You have ultraviolet and you have visible light. Well, that stuff comes into the atmosphere and gets absorbed by molecules on the way in, but for greenhouse gases, that's going to contribute to greenhouse gases, but not the main thing. Then you have that coming in and warming the surface of the Earth. So that visible light and that ultraviolet light gets changed. Ultraviolet light is high energy stuff relative to the other stuff. It gets absorbed by the rocks and the trees and all that kind of stuff in the Earth's surface, and it changes to infrared, which is much lower energy. That then gets reflected back out into the atmosphere, and it's the infrared light that molecules absorb well. Molecules can absorb ultraviolet light, they can absorb visible light, but the infrared is the important one because infrared is heat. If you have infrared shining on your hands, that's heat. If you have ultraviolet shining on your hands, you can't feel it so much. You get a sunburn eventually, but you can't really feel it. But one of the things about our skin and about things is ultraviolet is heat. So you get visible and ultraviolet coming down, hits the surface of the Earth, gets infrared. That infrared then gets reflected back into the space, so the Earth radiates heat. Some of that heat gets absorbed by molecules and then gets, rather than going out into space, gets redirected. Some of it out into space, some of it parallel, some of it back to Earth, all different directions, random directions, depending on how the molecule is oriented. So that means then that every single molecule in the atmosphere of Earth is going to contribute to greenhouse effect. So long as that molecule can absorb IR, it's going to contribute to the greenhouse effect. So why is Dr. Jan talking only about CO2? That's not the main part of the atmosphere, and we'll get into what the atmosphere is made of in a minute. But why is he talking about just CO2 and not all of the other molecules, and not even the most predominant molecules in the atmosphere? We'll talk about that in a minute as well. But first, let's just take a quick look at the atmosphere. The atmosphere is a very complex place. There's a lot of chemistry that goes on in the atmosphere. The chemistry that goes on in the atmosphere is very different at the top than at the bottom. But I love this slide for a couple of reasons. One is it separates the atmosphere into different layers. But the other thing is, I just love this thing, this thing. What does this red line represent? I need an answer, I can't go on.
It's some kind of path.
Yeah, but what does that represent? If you look at the graph, yeah, temperature. And this is something, I just liked it just because it's my own personal quirk. Because if you look at this, the temperature profile of the atmosphere, what does it say? Well, it says down near the Earth, it's pretty warm, right? And then as you go up, start climbing mountains, whatever, it gets cooler. We're familiar with that, right? That's an everyday occurrence. You know, you go climb a mountain, it's colder at the top of the mountain than the bottom of the mountain, right? Then as you go up, kind of plateaus out, and then what? It gets warmer again? Then colder again, and then way at the top of the atmosphere, look how hot it gets. Oh my goodness gracious. And I love this slide because it's true, but it's not true. Right? So if you're up in outer space, almost outer space, you're up here. It's really, really hot, right? So on the top of the atmosphere, right before you're jumping off into space, this graph says it's super hot. Is that true? No. It's really cold, right? So why does that graph say that?
Is density an issue?
Yeah. And this is the thing that I like, just because I'm a chemist, is that the molecules, the ions, whatever's up there, are really hot. What does that mean? It means they're moving fast. They're moving fast. They have a lot of velocity. But there's no molecules there. It's basically a vacuum. So it's really cold because the power density up there, there's nothing there, so it's really cold. But if you happen to run into a particle, that particle's really hot. And the same thing happens in outer space when NASA's taking satellites out. They'll often say that they measure the temperature of 4,000 Kelvin or something, 4,000 Kelvin. Well, why doesn't the spaceship melt? Because the particle that hit the spaceship is 4,000 Kelvin, but there's very few particles that hit the spaceship, so the spaceship never gets warm, right? But that has nothing to do with this talk, but I just love that thing. Okay? Okay. Oops, I hit the wrong button. Okay, what's in the atmosphere? So, Dr. Jan was all about CO2, but what else is in there? Well, the atmosphere is made up of nitrogen, almost all nitrogen, right? Roughly 80% nitrogen. And again, these numbers are rough numbers, okay? They're not exact. So, about 78% nitrogen, 21% oxygen, thank goodness. Water, we always forget about water, but water, again, 0 to 4%-ish of the ranges that I found. Next is argon, a little less than 1%. Now, finally, we have CO2. Dr. John was talking about over 400 ppm. The resource I had for this thing said about 380, so it's pretty close. Okay. Again, 0.038% or 380 ppm, same thing. Methane, another greenhouse gas, so put that on there. About 1 ppm, so rather than 380, it's 1. And then N2O, again, a form of nitrogen, but this one is much more reactive and much more prominent in the greenhouse effect. Only about 0.3 ppm. Okay? So, of all of these gases, why pick on CO2? Why pick on CO2? Because CO2 is the one that is changing the most. That is the one that's changing due to all of the industrial stuff that goes on in society now on Earth. The other ones, is nitrogen going to change from 78%? No. Is oxygen going to change from 21%? Hopefully not. Okay? Argon, definitely not. Not very much. So these things are all basically fixed. The ones that can change are the last three. CO2, methane, and the N2O, nitrous oxide. Those are the big greenhouse gases, well, three of the big ones, that are actually changing, the other ones don't. Okay? So why do we pick on CO2 and not the other ones? Because that's the one that is changing, that's the one that's responsible for any change in the greenhouse effect. Well, there's two other things. So the other part of this whole issue is not only how much is there, but the other part is how well does the molecule absorb IR. Not all molecules absorb infrared at the same rate to the same level. And so there's a factor for that. I call that the GWF, global warming factor. Okay? And when they make that up, they've set CO2 as 1. So if you just, it's an arbitrary number. But CO2 is 1. So it absorbs IR, infrared radiation, at a rate of 1. Methane has a global warming factor of 30 to 35. So it's 35 times more efficient at absorbing IR radiation than CO2 is. And then N2O, 250 to 300. It's 250 to 300 times more efficient at picking up that IR radiation. So it turns out that CO2 is not particularly good at absorbing IR. It's not particularly good at doing greenhouse effect stuff. It's only got a factor of 1. So why is it responsible for 82%, according to the reference I had there, of the increase in global warming? Because there's so much of it. Remember that that's 400 ppm roughly. The methane was 3 or so, I forget, and the other one was about 1. Okay? So, again, according to the source I had, it said CO2 is responsible for about 82% because there's lots of it. It's not too terribly efficient, but there's lots of it. Methane, which is probably, if I were to guess, I'd say that's going to increase from 10% simply because we're starting to use a lot more methane than we used to, right, with all the frack gas and all that kind of stuff. And the other thing with methane is that they're starting to have problems with the storage of it. I've read a number of articles where they have, what they do is they take and they store these huge amounts of methane in natural places. And I don't know, it's like under the ground. They stick them under, that's what it is. They stick them under the ground and store them. And in California, they had a huge problem just last year where the thing started leaking. And they had no way to stop the leakage, and so all that methane just went into the air. And nothing you could do about it. And so as you use more and more methane, I suspect that will increase to some extent. And again, that's important because it's a much more efficient global warming gas than CO2 is. And again, why? Because it's how efficient the molecule absorbs IR. So next slide is I didn't want to go through all of the different absorptions of the molecules, but I just want to show you one. So this is methane. And this is the infrared spectra for methane. Pay attention, because this is coming up in organic later on. Okay? But what this shows is that the wave number is related to energy. So this is higher energy, this is lower energy. Methane absorbs some IR here and here. If you put IR light, if you shine infrared light on methane and you shine with this energy here, nothing happens. It can't absorb the energy. It can only absorb the energy here and here. When you have infrared coming from the Earth, it's essentially going to exhibit infrared at all frequencies. So this one and that one will be absorbed, all the rest of them won't. So there's two factors to how efficient a molecule is for global warming. One is where does it absorb, how much can it absorb, and the other one is how efficiently it can absorb that radiation. Turns out that methane can only absorb in basically 2 spots in this spectrum, but it absorbs super efficiently, and so it has a factor of 35. Whereas CO2, because of the shape of the CO2 molecule, linear, it can't absorb IR as well, and it can't absorb it. So even if you have the right energy for CO2, it doesn't absorb it as well. It can't handle as much energy. And then what happens is that the molecules absorb the IR that's coming from the surface of the Earth, and that goes into modes of the molecule, and this is why they can only absorb certain energies. So in the methane's case, you have methane, the formula for methane is CH4, 1 carbon, 4 hydrogens. When this energy is absorbed, what happens is you have on the carbon atom, hydrogen atoms. What happens is they start to do this. So the molecule goes into a vibrational mode of the molecule, and it's going to do that for a little while, and then all of a sudden it'll just stop and kick the energy back out. When it kicks that energy back out, it kicks it out randomly, any kind of direction, some of which will be headed out to space, but a lot of it won't. And that's energy now that is left in the atmosphere that would have radiated to space previously. And that's how molecules contribute to global warming from a chemical point of view. Okay? And again, that's all of these molecules we talked about have infrared spectrum. I'm just going to show you the one example. So if you take a look now at the accumulated IR spectrum, again, notice it's very similar to the other one with the wave numbers on the bottom directly related to energy. And notice what you see. These are the absorptions. So although CO2 is not an efficient user of IR, global warming factor only 1, this peak is huge for CO2. Why? Because there's so much more of it. Remember, there's 400 ppm roughly versus a few ppm for the other ones. So it's 400 times more prevalent. So you have, these are fluorochlorocarbons, which have now been banned, basically. So these are going to go down over time. But then ozone, top of the atmosphere, again, these things actually destroy the ozone, which is why they got rid of these. You have the N2O I talked about in the CH4. And notice that these things are kind of down in the grass here, down in the noise spectrum, but they're contributing a little bit, major contributor. And this is, again, why Dr. Jan was talking all about CO2. So let's go talk about CO2. And again, remember that first graph that had the atmosphere and the temperature thing on it? This is another one of these things that just lights my fire. I love this particular graph because, again, here's the CO2 over time, the black line. And the red line represents seasonal changes in CO2. And the first time I saw this, I was floored with this thing because I said, it's a sinusoidal wave. Why would it ever be a sinusoidal wave? Why does CO2 go up and down? And it turns out that this is proof of photosynthesis. Because it goes up in the winter when the trees aren't doing anything. It goes down in the summer because the trees are taking CO2 and incorporating into their structure and growing, and the grasses and all that other, and the bacteria, the plankton. And so you can actually see the seasons reflected in the CO2. But notice the trend. Up. Dr. Jan said 400. Well, okay, this graph says a little bit higher. Okay. Oops. Okay, why? I only have 2 more slides. And again, this is chemist's point of view. So why? Well, where does the CO2 come from? Almost all of the CO2, that's, again, man-made, right? So we're forgetting volcanoes and natural sources. But all the CO2 that's man-made is coming from combustion. Combustion of what? Some kind of hydrocarbon. So, is it heating oil for your house or for the power plant down the road? Is it coal? Is it methane, natural gas, heating your house, using your stove or running the power plant? Or is it gasoline, running your car? So from a chemist's point of view, I said, you know what, let me just do a quick calculation, and let me just use gasoline. Okay? So gasoline is a very, very complex mixture of hydrocarbons, very complex. But to simplify it, we all know that gasoline has an octane rating, right? So let's just deal with octane, because it's complicated, but octane's going to be close enough. So my question is this. If I burn a gallon of gasoline, so I got my big truck, and it gets 15 miles to the gallon, and I'm going to go to the corner store to get my Snickers bar, and I'm going to drive back, I just spent more on gas than on the Snickers bar, right? At least I hope. And I could easily have burned a gallon of gas. Well, how much CO2 is actually produced when you burn a gallon of gas? Estimate. So, first you need the chemical formula. Octane, 8 carbons, C8H18. Combines with oxygen to make CO2 and water. And when you burn any hydrocarbon, be it oil, be it methane, be it gasoline, be it whatever, it always makes CO2 and water. And notice the CO2, but what about the water? We never pay attention to water in global warming. It varies all over the place. But water, it turns out, is actually a very, very efficient absorber of IR. It's really, it's in fact, if you have water in IR spectrums, it screws up the whole spectrum because it absorbs too much. So water is a contributing factor too, as well, but that's more easily mitigated. Okay, so 2 moles of octane react with 25 moles of oxygen to make 16 moles of water and 16 moles of CO2, 18 moles of water. Before I take a look at the calculation, let me just point out, the amount of oxygen necessary to burn this thing is incredible, right? You need 25 times as much, on a mole basis, of oxygen relative to 2 for octane. And some of the other components in gas are actually higher than 25. So every time we're burning all these things, we're really using up the oxygen of the planet. So far, doesn't matter. Why not? There's so much oxygen in the atmosphere that it hasn't had effect yet. Okay. So in order to do this calculation, I had to make a couple of assumptions. One is that that's the equation that governs it, and that's close enough for us. Also have to get some kind of temperature, so I picked, room temperature kind of thing, 25 degrees Celsius, 70, 75 degrees Fahrenheit. And we'll do it at atmosphere temperature, so we'll do it on the surface of the Earth. Okay? And the density of gasoline is about 0.7, and when I did that, I came up with this. So 1 gallon of gas produces 4,500 liters of CO2. That's at ground level. As that CO2 rises into the atmosphere, the pressure drops off, that's going to expand, and that's going to get bigger. But when I did this calculation, I was floored. 1 gallon of gasoline is how big? Like that, right? How much CO2 does that put out? We'll call it 2,200, 2,200 2-liter bottles of Coke. 2,200 2-liter bottles of Coke, roughly. So we'll call it 2,000. Imagine if I came in here with 2,000 2-liter bottles of Coke and put them on the front table. Guess what? Ain't going to fit. Right? Huge volumes. Again, the reason for that is that gasoline's a liquid and CO2 is a gas. But isn't that amazing? 1 gallon of gas. Okay, now we think about this and we say to ourselves, how many cars are on campus today? Right? Each of those cars had to drive here and drive home. 1 gallon of gas, 4,500 liters. Think about multiplying that by the number of cars, by the number of miles they drove, the gallons of gas that they used, and the numbers are phenomenal. That's just OC, SUNY Orange. Think about now in general, and that's just cars. When you now factor in the power plants and everything else and all the factories and everything else, think about how much CO2 is actually being produced. Huge amounts. The good news? The atmosphere is huge. So that amount, it's difficult to change. The bad news is, we've managed it. Right? Over the last 100 years, right, Industrial Revolution about 1900, so now 2017, over that time, we have managed to push the CO2 from whatever the historical level is, I think 200 ppm, is that reasonable?
290, I think.
290, up to 400-ish. Is that going to slow down or stop anytime soon? No. And then the other thing you want to just throw this out there, because everybody's saying, well, let's go solar. Let's do wind power. But don't forget, now those will be better probably, but you have to manufacture those. Manufacturing those takes, and it's going to produce CO2. And pollution and all that other stuff. So even that's not really a penance. And how long do they last? And so everything has an impact to some extent or other. Certainly that's going to be better, than just burning like we're burning now. But So, I think from a chemical point of view, is global warming real? Well, obviously it's real, right? Because, I said it wrong. Is greenhouse a real effect? Absolutely, positively a real effect. Is global warming a real thing? Well, it's early in the game from the point of view of changing temperatures, right? But definitely the Earth is, from a scientific point of view, is definitely warming up a small amount. It's going to continue. And then the rest of it is politics. Because the rest of it's money. It's all about money now. It's all about spending money to try to mitigate that effect. But the question is this. If you don't do something, what happens to the temperature? It goes up. What's going to happen when the temperature goes up? Nobody really knows completely because it's complicated. But we do know some bad things can happen. The weather patterns are going to change to some extent. Is it worth the risk? Again, a political question.